Let v1 be the vector 1, 2, 3, and v2 is the vector 4, 5, 6. We would like to find v2 cross v1. So the cross product of two vectors in 3 dimensions in R3 is given by the determinant of a 3 by 3 matrix. The 3 by 3 matrix will have I, J, and K, the standard unit vectors in the X, Y, and Z directions in the first row, and in the second row you'll have the first vector in your cross product, that will be v2, and in the third row you'll have the second vector in your cross product, that would be v1. So v2 is 4, 5, 6. Let's make a little more space there. And v1 is 1, 2, 3. So we need the determinant of this matrix. Now usually a matrix just has numbers in it. So this is kind of a makeshift determinant simply for the purpose of computing a cross product. And this cross product is going to give us a vector that is perpendicular to both v1 and v2, as long as v1 and v2 are themselves not parallel. So if we have two non-parallel vectors, v1 and v2, then the cross product will give us a vector that is perpendicular to both of them. Okay, so let's see if we can calculate this cross product. So this determinant, one way to calculate a determinant is to do what's called a Laplace expansion across one of the rows or down one of the columns. So with this particular configuration, it's typical to do the Laplace expansion across that first row of vectors I, J, K. So the way that works is we just have to go plus, minus, plus. We write down the vector itself, I, and then times the determinant of a smaller matrix. You remove the row and the column of I. Remove the row and the column of I, and you get a smaller matrix, 5, 6, 2, 3. And that's the matrix that we need the determinant of. And then you have to do minus J that was 5, 6, 2, 3. And then you have to do minus J times the determinant of a smaller matrix. And again, you remove the row and the column of J, and that's the matrix 4, 6, 1, 3. 4, 6, 1, 3. And then you do plus K times, again, the determinant of the matrix, where you remove the row and column of K. And that will give you this little matrix here, 4, 5, 1, 2. And now the determinant of a 2 by 2 matrix, let's just say it's got 4 numbers in it, A, B, C, D. You multiply the diagonals, A, D, B, C, and you subtract. So this is I, the vector I, times the number 15 minus 12, which is 3. And then minus J times the number 12 minus 6, which is 6. And then plus K times the number 8 minus 5, which is 3. So this is 3I minus 6J plus 3K. So 3, negative 6, 3 is our cross product. And that vector is perpendicular to both of these. Let's just check that. Let's just take the dot product of this vector with the vector 1, 2, 3. We should get 0. And we'll take the dot product with the other vector as well. And we should again get 0. 3 times 1 is 3. Negative 6 times 2 is negative 12. 3 times 3 is 9. 12 minus 12 is 0. And here, 12 minus 30 plus 18. 12 and 18 are 30. Minus 30 is 0. So this vector is perpendicular to both of these vectors. And that's what the cross product does for us. Also, the cross product is sensitive to the order. If you were to switch this order, then that means that you would switch these two rows and you would get exactly the negative of our answer here. So what I'm saying is if you calculated V1 cross V2 instead of V2 cross V1, then you would get the negative of this answer. You would get -3, 6, -3. So the cross product operation is not commutative. In fact, it's anti-commutative. Okay, that's a little bit on the cross product.